Hello everyone, thank you for taking the time to join today's webinar. Today we're going to focus on hydrogen flow measurement, safety and compliance. The TÜV-SÜD webinars are sponsored by the UK Government's Department for Science, Innovation and Technology, or DSIT for short. A recorded version of this webinar will be made available to you after the broadcast is finished. This will include the Q&A session that we have at the end. We'd love to hear from you, so please submit your questions any time during the webinar. You can find the Q&A panel on your screen and your questions won't be seen by any other attendees. We'll do our best to answer as many as we can, but if we do run out of time, we'll follow up on any unanswered questions by email. My name is John Dodds and I'm a bid manager, and I've spent the last almost 23 years at TÜV-SÜD working as part of the sales and business development team. As I mentioned, today we're going to be talking about hydrogen flow measurement, safety and compliance. Here to lead the discussion is your presenter, Dr. Madhi Sadri. Madhi's role here at TÜV-SÜD involves research, development and consultancy in the field of clean fuels and flow measurement for businesses, as well as being part of European and British funded projects on metrology. So, Madhi, if you're ready, I'll hand everything over to you now.
Great. Thank you very much, John. Okay, hello everyone, and welcome to this webinar. I'm going to cover safety and compliance for hydrogen today. So what I will cover will be very general. Basically, it applies to many hydrogen systems, including flow metering systems. Let's start from the background of hydrogen. Hydrogen was discovered in 1766 by the British scientist Henry Cavendish. He discovered it when he was combining mercury and acids. He noticed that there were some bubbles of gas and it wasn't any of the known gases at the time. Later on, the French scientist Antoine Lavoisier initially called this gas combustible air. Later in his experiments, he could produce water from hydrogen. So that's where the name hydrogen basically comes from. Hydrogen basically means water generator. So let's start and look at hydrogen properties, because it's really important to know the properties of hydrogen if we want to focus on its safety. Hydrogen is very similar to other small hydrocarbons like methane, butane, and propane. So all of these types of gas are combustible, they are odorless, they are non-toxic, and they are non-metallic. When we come to safety concerns, all these types of gas cannot be detected by human senses. Like, for example, if there is a leakage of hydrogen, we cannot smell it, as well as like the leakage of methane, butane, or propane. Just the only thing is that with other types of gas, such as natural gas or methane or propane, for example, they can easily add odorant to them. With hydrogen, it's actually difficult to add an odorant because hydrogen is very light and the odorant can get separated from the gas. So finding an odorant that can work with hydrogen is difficult. And also these gases are not harmful to health as long as they don't dilute the oxygen in the atmosphere to a dangerous low level. Hydrogen is the smallest molecule in the universe. It has a very low viscosity. So because it has a low viscosity, it has a high leakage rate. So a system that is tight enough for other types of gas, such as natural gas, might not necessarily be tight enough for for hydrogen. So it is very important to test such a system with like small atoms or a small molecule, something like helium. And hydrogen has a strong tendency to diffusion because of the small size of the molecule. So does it mean that we cannot store hydrogen? Well, that's not the case. We've been storing hydrogen for over 100 years. So what happens is that normally some hydrogen diffuses through the walls of the storage system, but because the diffusion is insignificant, we don't lose that much hydrogen, and also outside of the boundaries of the system, the hydrogen is not to a concentration that can make an explosive mixture. Okay, let's move on to the safety considerations and some other behavior of hydrogen. So I will cover dispersion, fire behavior, explosion protection, high pressure risk, and material compatibility in the next section. The first question maybe is hydrogen explosive? Well, I can say yes and no. On its own, hydrogen is not categorized as an explosive substance because its molecules are stable. But hydrogen, when it comes in contact with an oxidant, like the oxygen in the atmosphere, it can make an explosive mixture. So this is the triangle of explosion or fire. We need to have three elements for a fire or an explosion to happen. So we need the flammable gas, which is hydrogen. We need oxygen, and we need ignition energy. So even if one or two of these elements don't exist, there will be no explosion or no fire. So based on that concept, we can have measures in place to prevent any fire or any explosion. Protective measures normally are categorized under these three different levels: primary explosion protection, secondary explosion protection, and tertiary or constructive explosion protection. At the level of primary explosion protection, we normally try to prevent the formation of any explosive mixture. So examples of that is proper ventilation in your workplace, inerting of the system, and gas warning devices that should be in place. So that's the first step. We always want to make sure that there is no leakage, there is no possibility of an explosive mixture to be formed, and if there is one, put proper measures to prevent the hydrogen to get trapped there and get to the concentrations that are dangerous. So ventilation is actually very important for hydrogen. I will cover that more in the next slide. Secondary explosion protection is the next step. That's when we make sure that to avoid any ignition coming in contact with the possible explosive mixture that can be formed in our workplace. That's the examples of that is the classification of zones, ATEX devices, and lightning protection. So if you work in an environment that there is a possibility of the formation of an explosive mixture, you need to have those measures in place. And then finally, tertiary or constructive explosion protection is when we try to minimize the effect of a possible explosion. That can be explosion-proof design of the system, explosion venting, and explosion suppression. So in case that there will be an explosion or fire, we want to minimize this damage. So that's basically the last step. So let's take a look at hydrogen dispersion behavior. Ventilation is very important for hydrogen. I can say even more important than other types of flammable gas. Why? Because hydrogen is lighter than air. When you have a leakage of hydrogen in open air, it quickly rises and just escapes from that space around the leakage point because it's lighter than air. So if we are in a confined area, the leakage of the hydrogen that has leak, it quickly rises and accumulates under the ceiling, and then if it has time, it diffuses downwards and makes a very dangerous atmosphere there. So if you have proper ventilation, it is very likely that hydrogen escapes easily. Its fire behavior is very different from gasoline. So on the right-hand side, we have a picture that shows a fire by gasoline. And on the left-hand side, well, I'll explain about the left-hand side because we have two flames there. So let's start from the fire by gasoline. Fire by gasoline spreads along the ground because gasoline is heavy, so it spreads over the ground. It has a strong heat dissipation. So if you are near a flame of gasoline, you can easily feel it. It has heavy fumes. So as you can see on the right-hand side, there are black fumes that are very visible, and the flame continues to burn for an extended period of time after you have stopped the source of the fuel. For hydrogen, however, so let's focus on the picture on the left-hand side. So you can see in the picture there is a tank that has hydrogen inside it, and then there is a flame under it. Well, that's the picture from a bonfire test that is being done on this storage system. So the flame that you see there is not a hydrogen flame. Basically, the hydrogen flame is there, but you cannot see it. That's one of the characteristics of a hydrogen flame. If you have a flame of pure hydrogen, it is basically invisible. So there is basically a flame of hydrogen there, but it is hardly visible. If you focus so hard on the right-hand side, you will be able to see a steep flame directed upwards, like where the trees are. It's very difficult to see it. So that's the first characteristic of a hydrogen flame. So it's invisible. It expires without gas supply, similar to other types of flammable gas. It has a very low heat dissipation. So it can't be felt as easily as fire by gasoline. And there are no fumes, as you can see here, that can be seen. So you can imagine that when we have a flame that cannot be seen, it's hard to be felt, and there are no fumes that you can see. So basically, not much signs that you can just see or feel that there is a flame in your environment. It can create a very dangerous environment because you can unintentionally get too close to the fire without knowing. So the flame is basically there in this red area. Other characteristics of the fire behavior by hydrogen is maximum flame speed, which is approximately 8 times as hydrocarbon-based gases. So it means that if there is a fire, it spreads way faster, and then that increases the risk of detonation. That can cause chain reaction. So it can cause like a rise in pressure and temperature over a wide area. As I mentioned, it's barely visible and it has a low heat dissipation. That means we need to have proper detection, flame detection instrument in place. So hydrogen flames cannot be seen, but they have higher levels of ultraviolet radiation. So what that means is that we can use ultraviolet imaging cameras, we can use thermal cameras, or we can use water mist to detect a hydrogen flame. I talked about its radiation below. Does that mean that the flame is less dangerous than other types of flame? That's not the case. The flame temperature can go up to 2000 degrees Celsius, and the height can go up to 30 meters. So it is not less dangerous than any other type of flame. So this is a picture of two imaging cameras, as you can see. So on the right-hand side, we have a propane flame, and on the left side, hydrogen flame. So they can easily show detect the flame. Another way that you can use, actually, and it has been mentioned in the ISO standard, is just using a strobe room. So as you can see, it has even been mentioned in the international standard ISO 15916. So basically, if you suspect that there is fire in a place, what you can do is to just hold something like a strobe room in front of yourself, and then if it catches fire, that means there is fire there. The next slide is about the ignition limits of hydrogen and its comparison with methane and propane. So the vertical axis is the ignition energy required, and the horizontal one is fuel concentration. We have an LEL, or lower explosion limit, and we have an upper explosion limit, or UEL. So as you can see, the envelope for hydrogen is pretty large, while the envelope for methane and propane are way smaller. However, the lower explosion limit, or LEL, for all of them are pretty similar. So does that make hydrogen way more dangerous because its UEL is much higher than the other two types of gas? Well, that's not the case. Basically, let me explain this for people who might not be familiar with this envelope. So inside this envelope is where a fire or an explosion can happen. So with the LEL, that's basically the first point that we get to when we have a leakage of a flammable gas. So like for hydrogen is 4% of hydrogen, and up to 75% hydrogen in the atmosphere, we can have a fire. For methane and propane, the LEL is very comparable. So because when there is a leakage, we first get to LEL, that means that it doesn't really matter that the range is larger for hydrogen. But on the other side, on the other hand, you can see that the graph for hydrogen comes way lower in terms of the required ignition energy. So the ignition energy that is required for hydrogen to make an explosion or to a fire is lower than those two types of gas. So that's basically a safety concern that we need to keep in mind. Another characteristic of hydrogen, which is very different from these types of gas, is its Joule-Thomson effect. Hydrogen has a negative Joule-Thomson effect. What does that mean? So for a gas like methane, or most types of gas, when we have a sudden expansion, the temperature of the gas drops. For hydrogen, around the room temperature, that's actually the opposite. So if there is a release of hydrogen and its pressure suddenly drops, its temperature actually rises. So as an example, if its pressure drops from 200 bar to 1 bar, its temperature from room temperature can go up by 6 Kelvin. And this is not linear. So if the pressure drops, for example, from 700 bar to 1 bar, the temperature can rise over 50 Kelvin, which can be pretty dangerous. The next slide shows a comparison between vapor pressure of hydrogen and methane, butane, and propane. So as you can see, hydrogen has a small vapor pressure curve, and its critical point is basically below 50 Kelvin temperature. What that means is that it is basically not possible to pressurize hydrogen and just by applying pressure at room temperature make it liquid. So it is not liquefiable under pressure at room temperature. With methane, and as you can see, that doesn't get to the room temperature as well. With propane and butane, they are liquefiable under pressure at room temperature. But even the difference between hydrogen and methane is huge in terms of what temperature is needed for making it liquid. So we need a very low temperature for hydrogen to make it liquid, and basically that's the only way that we can make it liquid. So we have to reduce its temperature to a very low temperature, which is, I think, minus 253 degrees Celsius. Yeah. So this is like a comparison between the boiling point of hydrogen and some other substances. So as you can see, hydrogen is even lower than oxygen and methane, and we need to get to that temperature to have liquid hydrogen. So dealing with liquid hydrogen can be dangerous in terms of getting frostbite. So you should be careful with that if you have enough safety measures in place if you are dealing with liquid hydrogen. The next danger that can hydrogen have in our workplace is when it is stored as compressed gas. So let's start from the left side. You can see a storage system there that has a 5 cubic meters capacity and is pressurized to 7 bar. Such a storage system that is like the pressure is not too high, but it has an energy equivalent to 3.5 million joules. That is equivalent to a car that has a mass of 2.5 tons and moving at 190 kilometers per hour. So you can see what a huge energy that is. And if it is released, then it can cause severe damage. That is also equivalent to a truck that is 12 tons and moving at 86 kilometers an hour. So all this energy is equivalent to a very small typical type 4 vessel that is used for the storage of hydrogen. And like the pressure in these types of vessels can go up to 700 bar. Basically, in most cases, their nominal pressure is 700 bar when they are used, for example, in hydrogen vehicles. So if it is just pressurized to 350 bar, that will have a similar amount of energy stored in it. Another safety concern with hydrogen is hydrogen embrittlement of materials. Hydrogen can cause embrittlement in 2 different ways. So the first way that it can cause it is when we are dealing with liquid hydrogen. Because it has such a low temperature, basically that temperature makes reduces the ductility of any material that comes in contact with that hydrogen. And then it can increase the risk of cracking and the failure of the material. The other mechanism, the damage mechanism of hydrogen, is just hydrogen embrittlement itself. I will explain this in the next slide more. Just what I need to mention here is that if you need to find out which materials are suitable to be used with hydrogen, and see just the compatibility of materials with hydrogen, you can refer to these two ISO standards. One of them is for compatibility of steel and metals, and the other one is for polymers. So let's look at the mechanisms of hydrogen embrittlement. Hydrogen has two different phases. It has a molecular phase and it has a atomic or ionic phase. When hydrogen is in the form of molecules, it's basically uncritical. It doesn't make that much damage to any system. But when these molecules come in contact with the surface of or the boundaries of the system, because of those interactions with the surface, the molecules can split into two ions. And these ions, because they are very small, they can easily diffuse into the structure of the material. So when they diffuse into the structure of the material, they can go between the atoms of the metal and then reduce the cohesion between metal atoms. That will cause ductility reduction in the metal, and then finally it can cause cracking in the metal and the material will fail quicker. So if you are using a system with hydrogen, it is more likely that your system or your system components fail quicker than if you are using the same system with, for example, natural gas. So what is the effect of pressure and temperature on hydrogen embrittlement? Basically, if we have a higher pressure, we will have more hydrogen diffusion rate. So basically, it means more hydrogen will diffuse into the structure of the material and will cause more problems. So basically, if your system works at a higher pressure, there is more risk of hydrogen embrittlement. For temperature, is not as straightforward as that. So at very low temperatures, materials have low ductility, so that increases the risk of embrittlement. But at the same time, because the temperature is low, hydrogen diffusion slows down as well. So so that kind of somehow balances the reduction in ductility. At room temperature to moderate temperature, such as 300 degrees Celsius, that's the most dangerous range, basically, because hydrogen can diffuse very well at that temperature, and the ductility of the material is not as high as higher temperatures. So that's the most dangerous zone for hydrogen embrittlement. And then at high temperatures, because the ductility of the material is higher, there is a lower risk. And also the hydrogen that diffuses into the structure of the material can escape easily. This table has been taken from the ISO standard 15916. I've used 3 signs here, like there is a green sign tick that just shows that material is suitable to be used with hydrogen. The red cross means that it is not suitable, and the triangle means that it can be suitable, but under specific conditions. So you can refer to this standard if you want to check different types of steel and whether they are suitable to be used with CGH2 or gaseous compressed gaseous hydrogen or liquid hydrogen LH2. And then also you can check different metals in the same standard. So as you can see, like for example, aluminium and copper and their alloys are normally suitable to be used with hydrogen. The other damage mechanism of hydrogen is high temperature hydrogen attack, or HTHA. And this damage mechanism happens to just steel and happens at high temperatures above 178 degrees Celsius. What happens in this case is that, again, like similar to hydrogen embrittlement, the molecules of hydrogen come in contact with the surface, they split into ions, and these ions diffuse into the structure of the steel. When they diffuse in the steel, they start a reaction with the carbon in the steel, and then when they react with it, they make molecules of methane. So two things basically happen at the same time. The first thing is that the steel decarbonizes and loses its strength, and at the same time, the molecules of methane will make bubbles inside of the structure and will apply some internal pressure to the material. So basically, it can cause cracking and the failure of the material. Okay, the last part of this presentation is on regulatory compliance for hydrogen systems. So I will just very briefly cover the compliance after Brexit, UKCA and CE markings. Then I will just cover two of the most important directives and regulation sets that are relevant to hydrogen systems, including flow measurement systems. So they will be Pressure Equipment Directive and ATEX Directive that covers explosion protection. In the UK, we have the British Standard Institute, or BSI. BSI is the national standards body and represent UK in the international standardization organizations such as ISO and CEN. However, BSI is not the regulator in the UK. The regulator in the UK is Office for Product Safety and Standards, or OPSS, that works under the Department for Business and Trade. The responsibility of OPSS is to regulate all consumer products, well, except for some products such as vehicles, medicines, and food, that they have their own regulators. And OPSS is the national regulator for legal metrology. For a product to be compliant with regulations, well, there are normally different sets of regulations at different levels. There are regulations at an international level, for example, the regulations from the United Nations. There are regulations at the European Union level, and then there are national regulations. So depending on where your product is, or where you want to put it on the market, that product needs to be compliant with those regulations. So before Brexit, what we had was that we had, in the UK, we had the European Union directives that and regulations that we needed to comply with. But after Brexit, that has basically changed, and UK is not following those regulations, and it doesn't need to follow those regulations anymore. So after Brexit, the UKCA marking has been introduced in the UK. The marking in the European Union is called CE marking, and what that means is that when a product or a system that you have assembled receives CE marking, that means that that system is compliant with all the required regulations that applies to that system. So if you can get that marking, it means that your system is compliant and you can put your system on the market, for example. In the UK, after Brexit, UKCA marking was introduced, because before that, we just used CE marking. However, what I need to mention is that CE marking is still acceptable in the UK. So if you can show that the system is compliant with the EU regulations and receive CE marking, that will be acceptable in the UK. But the opposite of it is not correct, though. You cannot use UKCA marking in the European Union. So what I'm going to cover here is two different directives that apply to hydrogen systems. We have the European directives, and then we have the equivalent sets of regulations in the UK. Basically, they are almost the same. So what I'm saying applies to the UK and to the European Union. So in the European Union, it is called, the first one is called Pressure Equipment Directive. In the UK, it is called Pressure Equipment Safety Regulations, or PESR. Its scope is design, manufacture, and conformity assessment of pressure equipment and assemblies with a maximum permissible pressure over half a bar. So basically, if you have a system that has a pressure over half a bar in any part of it, even if it is in one component of it, your system, the component of your system and your entire system needs to comply with the Pressure Equipment Directive to receive CE marking, or with the Pressure Equipment Safety Regulations, or PSR, to receive UKCA marking. And then it can cover different types of systems, like whether it is a flow measurement system or any other type of system. You have normally two different ways to show that your system is compliant with the regulations. You can go through the European standards or the UK regulations, or you can go through another route through other codes and standards that exist, like international standards. But the second route that I mentioned, going through the equivalent standards, is more difficult. Why? You see it on the right-hand side, because you need to show that the requirements of those standards are equivalent and can that assure the same level of safety as the UK or EU regulations. So basically, it is easier to go through the route of UK and EU regulations. And then after that, you might need, based on the category you fall under, you might need a notified body in the Europe, as it is called, or in the UK, it is called a conformity assessment body. If you need it, so there is a third party that needs to come and confirm that your product is compliant. And if you don't need it, you can just claim it yourself, and then you can receive the CE marking or the UKCA marking. The classification on the Pressure Equipment Directive is based on these four factors. So it's based on the pressure of your system, it's based on the volume of your system, or if it is a pipe line, based on the diameter, based on fluid group, which can be flammable and toxic, which is fluid group 1. So hydrogen will fall on the fluid group 1 because it's flammable. Or fluid group 2, that is anything except in fluids in group 1. And then the physical state that can be liquid or gas. So hydrogen, again, can be any of them. Based on those factors, you determine which diagram you need to use to determine the requirements for your system. So for example, if you have a tank, as you can see, so a tank of a hydrogen gas, so the compressibility, so obviously let's assume that's compressed gas. And then the fluid group, as I mentioned, for hydrogen is 1. So on the left side, we get to diagram 1. If we think about a CgH2 vessel, for example. And then for such a system, we need to refer to diagram 1 to see the requirements for that system and what we need to comply with. So this is diagram 1 taken from PED. It is basically based on the pressure and the volume of your system. So if you use the pressure and the volume of your system on this diagram, you fall in one of these 4 areas. You can fall in category 1, category 2, category 3, or category 4. As you can see, for less dangerous systems, where there is a lower pressure or lower volume, you get a lower category, and then for higher pressures and bigger volumes, you get a higher number. So it means that the requirements for a higher category is actually more strict. So let me finish this. So based on the category that you determine here, you just go back to the pressure equipment directive and read the requirements, and then you need to make sure that your system will comply with all those requirements. So if you fall in a higher category, you should comply with just that category. If you fall in a lower category, you can comply with the requirements of that category or any higher categories, because obviously their requirements are more thorough. The second directive that I'm going to cover briefly is ATEX directive. This directive covers explosive zones and just how we need to protect our environment from any explosion. So in the Europe, it is 2 different sets of directives. ATEX directive that covers the 1999 that covers operation, such as design of explosion zones, and ATEX Directive 2014 that covers the product or the nature of the explosive zones. In the UK, the equivalent set of regulations is the Explosive Atmosphere Regulations, or UKEX. So ATEX basically determines different zones. I will talk about the zones more in the next slide. And then the requirements for the equipment that should be used in these zones, the equipment that are safe enough to use to be used in these zones, or the equipment that are not in the zones but just basically work to make sure the required safety exists in the zone. So based on ATEX, we classify we make a classification, and just different workplaces can classify under these 3 zones that are mentioned here: Zone 0, Zone 1, and Zone 2. Zone 0 is basically the most dangerous zone. and zone 2 is the least dangerous, but it's still an explosive zone. Zone 0 is, I just read the definition from the directive EN 679, area in which an explosive gas atmosphere is present continuously, so that's a keyword, continuously, or for long periods or frequently. Zone 1 is area in which an explosive gas atmosphere is likely to occur in normal operations occasionally, and then zone 2, that is less dangerous than the other two zones, is an area in which explosive gas atmosphere is not likely to occur in normal operation, but if it does occur, will persist for a short period only. So it's just less dangerous than other two types of zones. So these zones are for flammable gas. We have also zones for explosive dust. The equivalent zones for explosive dust are zone 20, 21, and 22. Those don't apply to hydrogen, obviously. And they have another directive, as is mentioned below the table. And then finally, the last slide of this presentation. So based on the zone that you determine, you need to determine what type of equipment needs to be used and what safety level you need for the zone that you're working in. So for zone 0, that is the most dangerous zone, you need category 1 equipment. Category 1 equipment has a very high level of safety. For zone 1, you need category 2, and for zone 2, you need category 3. Just one thing that you need to keep in mind is that if you need equipment for zone 0, you can only use category 1. But if you are working in zone 1 and 2, you can use their own category, or you can use a safer category. So for zone 1, basically, you can, for example, use category 2 and category 1. For zone 2, you can use category 3, 2, and 1, but the opposite of it is not possible because the safety requirements will not be met. Okay, that was basically the last slide of this presentation. So thank you very much, everyone, for being with us today. So back to you, John.
Thanks for that, Maddie. That was good. I mean, there's been a lot of questions come in during that presentation, so I think we'll just jump straight in, Maddie. Okay, first one. What's the biggest safety risk with hydrogen?
I'd say the biggest safety risk is an undetected leakage. And also another thing that I mentioned in the presentation is an invisible flame. So it is very important with hydrogen to just have proper equipment in place if we are working with hydrogen to detect a leakage, because as I mentioned, in many cases there is not a proper odorant to be used with hydrogen. So we can't feel it if there is a leakage. So we need to have proper equipment in place, like gas detectors, for example, and proper ventilation, because hydrogen rises and it can easily escape from the building if there is proper ventilation in place.
Yeah. Okay. Another question here on CE marking. How long will CE marking be valid in the UK?
Good question. I think initially the plan was to just introduce UKCA marking and just have a transition time when like all the regulations in the UK are being written and just being prepared, and the just the entire framework of UKCA. And then after that transition time, the government was meant to just to only accept UKCA. And I think they started to do that. So they determined the transition time, but I think it became clear that it's actually not that easy, because we were just so kind of all the regulations were so reliant on the European Union regulations that it was not that easy to just separate the regulations. So at the current time, they have extended the validity of the CE marking indefinitely, the government. So that might mean that it will be permanent, or at a point they might feel comfortable to just say UKCA is the only marking that we will accept in future.
Yeah, okay. During the presentation, you spoke about compatibility of metals with hydrogen. Has there been anything done on composites? This is an area that I've come across quite a few times myself, with companies looking to use composites for transportation and things like gas cylinders. Has there been anything done in that area?
That's a good question. Yeah, there are two different ISO standards. One covers metals and steel, and the other covers polymers. So I don't think there is anything on composite yet. There will be definitely information on what composites are more compatible with hydrogen. But I'm not sure if there is any international standard on it at the moment.
Yeah. Okay. Yeah, because I know it's an area that's coming up more and more. I've had a few people asking us, will we share the presentation after the game? As I mentioned earlier, we will be sending you an on-demand version of this webinar when it's finished, but we don't actually send you Maddie's presentation as such. Okay. Question here about flame length. Why up to 30 metres? What's the limitation or limitations from preventing a flame of a greater length?
Yeah, that's again a good question. That's not my area, but what I know is that the length is depends on the pressure and the flow rate at the nozzle, or where the hydrogen is being released. So when we start like at a low flow rate, the release of hydrogen is in a laminar form, and then with the increase in pressure and the increase in the flow rate, the length gets longer and longer. But then after some time, when we get to very high pressures and very high flow rates, the turbulency increases in that flow, and then that basically stops the flame from getting longer. So at a point, the flame, the flow is too turbulent to just make a longer flame, and at that point, basically the length of the flame becomes constant.
Yeah. Okay. Right. It's said that hydrogen systems almost always leak a tiny bit. Does this mean that any compartments of any hydrogen system can at least be classified as a zone 3?
Zone 2, yeah.
Does not form during normal operation, and that's what's your views on that?
Yeah,
so
there are
zone 2, did you say?
Yeah, there are guidelines on which parts of the system categorize under which zone. So it's not like even it's not even like your whole system is one zone. So you might have a system and different components of it fall under different zones. So yeah, there are guidelines. There are very clear guidelines on how to do the zoning.
Okay. Question here, is it true that high pressure H2 vessels are lined with carbon fiber?
Some of them. We have different types. So the type 4, yes, it has carbon fiber. Yeah.
Mm-hmm. Okay. Question here on detection and leakage. The detection of leakage with equipment requires functional safety requirements for devices. I'm assuming that's a question, not a statement.
Sorry, what was that?
It's talking about the detection of leakage with equipment. Does it require functional safety requirements for devices? I'm not sure about that one. You might need to email them and ask them after this presentation.
Yeah.
Let's see what we got. There's lots. They're all still coming flooding in, so there's plenty of questions coming in. Okay, you mentioned ability to detect a leakage. Is there already available reliable equipment to do this, considering the hydrogen flame challenges that you mentioned?
Yes, there are gas detectors that can be used. So gas detectors that can be installed in the building, or even portable gas detectors that the employees can have on them, and then they can detect the hydrogen leakage, or basically the hydrogen concentration in the atmosphere.
Mm-hmm. Okay. Does hydrogen speed rise above Mach 1 towards Mach 2?
Oh, that's a good question. I'm not sure about that, to be honest. Yeah.
Okay, sorry, we can get back to him on that.
Yeah.
Right, okay. There's loads of questions. They're still coming in. Keep putting the questions in. We will try and get back. We will get back to all the ones that we don't answer, but we're fast running out of time. Let's see. So thanks for joining us today. As I mentioned earlier, we will be sending you the on-demand version of this webinar after the event is finished. For attending this event, you've now earned yourself a 10% off discount from TÜV SÜD Academy on any training course. So all you need to do is quote the exclusive discount code, which is webinar_10. We would also like to ask for your input into a hydrogen test facility development that we are involved with, along with the Energy Transition Zone, the ETZ. Further information will be provided in a follow-up email, and I would urge you to take a little bit of time to complete that, respond to us. Your feedback will be invaluable as part of that project. Keep your eyes peeled for other webinars on this topic. You'll find it on our resources section on the website, which is www.tuvsud.com/UK. Please get in touch with us and let us know of any other webinar subjects you'd like us to cover. It's good to hear exactly what you're interested in. Feel free to get in touch with me via the email on screen, or send inquiries to info.uk@tuvsud.com. On behalf of myself and Maddie, thanks for your time today, and enjoy the rest of your day.